The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, a recap of last lecture. There are many terminologies in the last lecture. We basically start from the Boltzmann equation under relaxation time approximation. And we derived the expression for the charge flux, current flux, which current density, and also for the heat carried by the charge. And so we have the coupled equation for electrical transport. I have to, like I pointed out before, I use a different symbol, JE and JQ. JE is for electron, JQ in the book is for heat. And always the challenge is deal with the negative sign of electron. So I put a Q, small q, just for whatever is positive is for hole, negative, that's for electrons. And then I use a capital Q. So that's what I did in last lecture. And so we have those coupled equations, and those type of coupling is very common when you deal with, say, the transport processes. Here we do the electron and the heat coupling. As said, when you do piezoelectric and heat and mass transfer, there are all those type of relations. And if you generalize the gradient by the generalized entropy gradient as the force, then you have the uncircular relation between those coupling coefficients. In the generalized form, those coupling coefficients are equal to each other. But since we're not writing into the entropy, we're writing temperature. So L21 equals T L12 in this specific expression we use. And from this, it's natural to say when you have a temperature gradient, you also have, even in the open circuit case or any conductor or semiconductor, you have the feedback. You have voltage generated if you have temperature gradient. And the Peltier effect is when you have charge flow in the conductor, even if you don't have temperature gradient, associated with charge flow is the heat current, is the heat flow. And that's the Peltier heat, which is manifested itself when you put two materials together and form a junction. And because of discontinuity in this Peltier coefficient, you have cooling or heating at the junction. But fundamentally, it's an effect that happens in the same material, right? So we talk about the material properties, Seebeck effect, Seebeck coefficient, Peltier coefficient material properties. And similarly, Thomson effect is the Seebeck and the Peltier were actually experimentally discovered. But Thomson effect is not Kelvin predicted when he tried to unify and give us a general interpretation of what's the Seebeck and what's Peltier effect. And then he discovered there has to be a third effect. That's when you have a temperature gradient and the current flow at the same time in the material. Then you have distributed local cooling and heating along every point in the material. So the relation between those coefficients are Kelvin relations. And you can see there are a lot of relations. That's because all those expression, flux expression, is derived at least under the framework we're talking, the relaxation time approximation. You don't have to use that, but eventually those coefficients are all related back into the relaxation time, right? So we have, say, the relation between electric conductivity and thermal conductivity for charge, Wiedemann-Franz law. We have relation between Peltier and Seebeck effect, that's a Kelvin relation. we also have in the electrical engineering, say the drift diffusion equation, which is actually just the first term of that JQ. L11 is electric conductivity, and then when you write into the separate expression, right, when we split out the driving force for the current flow, which is electrochemical potential, they include the chemical potential and electrostatic potential. The chemical potential is related to the carrier density, so that's a gradient, that's a diffusion term. And electrostatic potential gives you the force, electrical force acting on the charge, so that drives the drift. So drift is measured with the mobility, diffusion is diffusivity. And again, the relation between diffusivity and mobility is the Einstein relation. And in fact, the Einstein relation, I commented, Einstein didn't do electron, he did the Brownian motion for molecules. And he has relation between the mass diffusivity and the viscosity. And that's special case. All those are special case is of the fluctuation dissipation theorem. So the fluctuation gives the Brownian motion diffusion, and dissipation is the viscosity, mobility, that's the correlation. So, so all things are tied together, a lot of terminology, but they are intrinsically all connected. And at the end of the lecture, we want to discuss the thermoelectric device. A real device is typically made of pairs of P and N, and you connect them electrically by, typically it's metal, and then say this is the basic construction unit, and you repeat them many times in a commercial device. And the reason for us for this, you connect many of them together, is because the typical ZT, say electric figure of merit, when you get a ZT, the largest case in commercial material, which is bismuth telluride base, right? The Seebeck is of the order of 200 microwatt per Kelvin, and the electric conductivity is of the 10 to the 5th ohm per meter. And the ohm per meter, inverse ohm per say is also Siemens, so it's Siemens per meter, or Siemens per meter, different units, right? So 10 to the 5th, so the material is actually very conductive. Metals electric conductivity is 10 to the 8th of the order. Yeah, I think it's in order, so 2 or 3 order magnitude higher than this semiconductor. Typically we use as a commented doping concentration is around 10 to the 19th, right? And if you make a silicon device in microelectronics, the doping concentration is typically 10 to the 17th, so 2 order magnitude smaller. So this is each leg is about a millimeter in commercial device, and the resistance, electrical resistance, is a milliohm. So when you have milliohm, you get a large current, and so you put say a lot of legs together to increase the electrical resistance, and that way your operation is easier. You don't have to have that large current operation. And the thermal conductivity is made of electronic contribution and phonon contribution, and this is of the order of 1 watt meter Kelvin. Okay, and this value is comparable to glass. Glass is 1.2, right? And this is a typical material is actually about 1.5. And so you want a material with a high electric conductivity, no thermal conductivity, and you want each electron carry a lot of heat. Seebeck is the entropy, average entropy carried per charge I mentioned, right? So that's the dilemma there. You have to play with the material, say try to it turns out that you change one, you also most of the time are changing the others. And there's a nice terminology to describe what you really want. You want, this is a so-called a phonon-glass. So for lattice vibration, you want it like a glass, which is amorphous, right? And amorphous material typically do not conduct the electricity well. So you want the electron-crystal, right? So phonon-glass, electron-crystal, but you want this happen in the same material. So this is where the challenge is, and trying to fool the material for the lattice vibration, you say this is like a very poor heat conductor, and for electron, it's like a good electric conductor. And typically, bismuth telluride, why it's good is because it's heavy. And when it's heavy, the phonon frequency is low, the group velocity is small, and intrinsically, the thermal conductivity is going to be lower. And the other way to use it to reduce thermal conductivity is by alloying, right? The mass scattering. For example, silicon, thermal conductivity is 150, germanium is about 90, and then when you mix the atom together, the difference, so the mass now, if you think about atomic chain, if each atom is the same, you got a harmonic vibration, very harmonic. But each mass point, you put a different mass, you know that string is not going to vibrate very well. And that's the mass difference scattering, alloy scattering. And that's the typical way to reduce the thermal conductivity. And of course, you want to do it to not to reduce the electric conductivity. Okay. So we discussed some of the typical characteristic of S sigma K. And if you engineer, let's say also, let's say most of you engineers. So what's important is to match. Okay, it turns out the device you can size differently, cross-section area, height, and you actually have to match the two sides because the analysis I gave is just one leg. When you put the two legs together, you'll see area length ratio has to be matched to get the maximum performance. So there are a lot of optimization at both materials level and also at the device level. Okay. Any questions? So if you look at the energy research, right, and right now there are a lot of course, great interest, and look, energy devices, there are not many stuff, right? A lot of people work on solar cells. A lot of people work on batteries. And the rest is you just say people all want to work on research, say energy related, so you suddenly say a lot of people now work on thermoelectrics, right? But actually, thermoelectrics is fun in the sense you really have to fool the material, right? And it goes into nonlinear regime, right? Everything is scattering. You want to control transport, you have to control the scattering. So it's both difficult, and if you like it, it's fun. Okay? Don't like it, it's a headache. When I got into thermoelectrics, the first thermoelectric program. So if you look at history, right? In 1821, Seebeck discovered the effect. Around the 1900, this is a parameter ZT was formulated. So how you make a generator, you need a material with high ZT. And around 1950, bismuth telluride was discovered. And that's when, so this was by Goldsmith. And when he discovered bismuth telluride, he said that he was just, he's actually very lucky. He said the first guess, he found it. He has a good physical insight that you need a heavy material. Heavy material turns out to also usually have better mobility, okay, charge mobility. And so we tried bismuth telluride and it worked. And so most commercial device was based on bismuth telluride. And then say for power generation, LASA was interested because it's solid state. And it's based on, but you have to go to higher temperature. Bismuth telluride is not stable. So they went to silicon. Silicon germanium is by the idea of alloy. That's the Russian scientist Alfei proposed that alloying can reduce thermal conductivity. So that led to develop silicon germanium. And silicon germanium has been used in most NASA flight for deep space missions. And they use nuclear waste, not nuclear waste, is nuclear fuel to generate the temperature difference, generate heat. And that has turned out for space is very reliable, and those generator work not very efficient, 5 to 6%, but they've been sending back signal some of those space missions over 30 years, right? And but for cooling, it's been based on bismuth telluride. Most terrestrial applications based on bismuth telluride. So commercial modules all used pretty much the material developed in the 50s, 60s. So there's not much research in this. And in in the 90s, right? So there are people. This is sometimes you also have to give credit to the program manager, and they start asking whether there is anything new in thermoelectrics. Okay, and one of the person they asked was Millie Dresselhaus, and Millie told me all the story, and she said it was not actually the military. It was a friend that kept talking. Somebody he ran in bus in a conference, and told her about thermoelectrics. And then when the military came in, asked her whether she had idea. There happened to be a graduate student looking for a research topic, and so he asked him to calculate the quantum well. Okay, so the idea of a quantum well, right? We want the S squared sigma electron better, right? If we look at the density of states of bulk material, right? That's a square root E relation, right? It's parabolic density of states, right? And this is energy. And remember, here is the EC. And depends on where you put the EF, right? I said the EF, if you put it here, if this is your EF, you'll dope it. And then we say the Seebeck is a measure of the average energy from the EF, right? So electrons, there's no electron below EC. There's a band gap, semiconductors. So most electron is in this region, right? Because of the Fermi-Dirac. The Fermi-Dirac is EF, at EF is 0.5 distribution. And the exponential decay very rapidly. So there are not many, so if you plot the per energy level, what's the occupancy? This is the Fermi-Dirac distribution. And this times this means this is EC, only a small portion. These are the portion that contribute to charge transfer. You look at the expression for electron conductivity. You have this homework of looking at the different product, right? So only electron near the EC bottom here contribute to the transport. The rest is too high energy. They're not filled. They're empty states there. Okay. So here is EC, and the problem with this is. Here, a typical parabolic band, right? There are not many carriers here. You look at it, right? This is the lowest density of states region. Not many energy carriers. So you did a density of states of quantum well. A quantum well is staircase, right? So now rather than this parabolic, you have a staircase, and of course you dope it again, and suddenly you got a lot of carrier here. Right? And so number of carriers is proportional to electric conductivity. So by making this sharp feature and then you control your doping, theoretically, you can get a larger S squared sigma. So this was the first paper published by Hicks and Dresselhaus. on this using quantum ideas to increase the S squared sigma. And Millie is, say, expert on bismuth. So she's an expert on carbon and bismuth. Carbon, she wrote an important paper. That's before carbon nanotube was discovered. She's been always talking about the carbon, and she wrapped that up and made that say, what if the energy level if you have a tube, right? So they skipped, the Nobel Prize skipped the carbon nanotube. She missed that, right? It went from the C60 that Richard Smalley discovered carbon 60, and last year went to the graphene, right? So the tube was missed. Anyway, so always do very conceptual, very simple, but made a big impact, right? And this is an idea that doing the say quantum well. And the other idea she had was say bismuth is a semi-metal. Okay, there's no gap, so you have an equal number of electrons and holes, and the Seebeck coefficient is low because they cancel each other. And so she say, okay, if you use this quantum size effect, that's your quiz exam, right? Electron move up, holes move down. So you turn that semi-metal into a semiconductor. So by using size, theoretically, all those are the possibility and the increase and really drove a lot of interest in this problem. So that was around 93. And at the year, I didn't know anything about thermoelectrics. I was working on semiconductor lasers. And I was worried that heat cannot get out. So this lasers has a lot of layer structure. And that's the quarter, if you recall, the Bragg reflectors, right? The Bragg reflector are the quarter wavelength layers. And I know that the mean free path, I thought this has low thermal conductivity. First, the thinking was the stop bands may reduce thermal conductivity. But say also the classical size effect, the mean free path could be larger than the thickness, and that can have lower thermal conductivity. So that's what I was interested in. But I didn't know anything about thermoelectrics until a program came out in '96. I learned this. Somebody say, "Oh, you should look at it." So I look at it. I say, "Ah, that's what they need." I say, "I can work on the denominator here, and team up with Millie and work on the numerator." So it took me 5 years to at least get to really know what is thermoelectrics. But we had fun in learning this. So there are a lot of current research in thermoelectrics, and many different ideas. The challenge is putting into real material. There are always things that you didn't quite realize, and most ideas don't work. Okay, but you have to keep thinking. And so there are a lot of progress made in the field. Okay, that's the comment on thermoelectrics. And now let's continue a few more things in this chapter. The question is, so in all the previous course, you probably heard about the local equilibrium, right? When you do heat transfer, talk about local equilibrium. What does local equilibrium mean? Right? So what is local equilibrium? And we know if an object is at the equilibrium, the per energy states, it obeys the Fermi-Dirac or Bose-Einstein distribution, right? And those distribution is isotropic. So this is F0. When we solve, right, F0 is isotropic. That's the equilibrium. In each, there's no net flux, because there are equal amount of heat or charge in any direction versus the opposite direction. So you don't have left flux. That's an equilibrium. And if you look at what the simplest form of a solution is tau v vx df d0 dx, right? This is the simplest form we used to derive the Fourier law, for example. And you plot this is under so this is how we derive Fourier law, right? So what really is given the flux is the deviation. This term is given the flux. F0 does not give you the flux. So if I plot the F itself in the forward direction, if this is my flux direction, and the backward direction is this. So what I have, the difference between the two is this section, that's the going forward, the left forward, and that's less going backward. It's these two contributing to the real flux. Okay? So what local equilibrium means is this deviation is small from the equilibrium. That's our assumption, right? When we do the perturbation F equals F0 plus G, this is the G, small, compared to F0. It's under that approximation we can derive the Fourier law, we can derive Liouville shear stress law, and Ohm's law. So local equilibrium still means there's no equilibrium. Here what I have is no equilibrium. Right? It's just a deviation from the equilibrium small. Okay? And so then we can ask, what are the conditions when this are no longer valid? Right? So if I go back to the Boltzmann equation under relaxation time is a V and d, let's say delta RF. I can say just consider the case of phonon, and the electron has a momentum term, right? So what I want is F minus F0 to be small compared to F itself, right? So I can think about the condition I have then is here, let's say tau v x df0 dx must be much smaller than f0. That's my condition for the perturbation. And then now if I do the order of magnitude, right, tau vx is the mean free path. Okay, so this order of magnitude is the mean free path. And f0, df0, dx, I can say f over the L. This is the order of magnitude I have, right? I'm not doing anything exact. I'm doing approximate derivative by f over f0 over L. L is your transport, whatever, gradient direction, right? I'm sorry? This is not an equation, this is a hand waving. Yeah?
T df dt. Tau df dt. Left.
Here?
Left.
Left. Oh, sorry. Yes, thank you. Yeah, here yeah. Okay. So what I have here is a hand waving, right? When you do order magnitude analysis, you write your gradient by say find a difference term and give you this is the order. And so what it tells me, one condition is the mean free path is much smaller than characteristic length. When the mean free path is comparable to the characteristic length of transport, your assumption is not valid, right? So that's one say condition. And this is where most of the time when we do micro nano, we're concerned where we fall into the size effect regime. when the mean free path becomes longer than characteristic length. In fact, you can do another, let's write mean free path df0, dx, I write the df0 dt and dt dx and less than the f0. Okay? And again, I do this over t. This is order of magnitude speaking. F0 cancel on those sides. dt dx, dt dx is delta t over L, much less than 1. Right? So what I'm saying here is the gradient dt dx, right, should be much less than, you can look at the temperature over mean free path. Okay. The reason I say this is for this case, it's very easy. If I do a film, the mean free path is longer than the film thickness, I will have a size effect. Right? And I'm concerned that the local equilibrium assumption may not be valid. But there's another case where my temperature gradient is too deep, right? If I have a transient transport and the temperature gradient varies a lot over one mean free path, right? Then this is say also a concern. Your say Fourier law may not be valid. And the third case is real transient, right? If I look at the transient term, this one I approximate df0 dt, right? And that also should be much smaller. So what say the time-wise, you can look at that this is a tau over t must be much smaller than 1. Relaxation time versus the transport process must be much smaller than 1. Okay? So these are the conditions for this local equilibrium assumption to be valid. And then when they're not valid, you say, I need to be varied. Right? And one way to one equation that's very famous called the Cantonian equation is trying to address this issue. Okay? And this is the the historical development for this transient problem is if you look at the semi-infinite object and you solve the heat conduction equation for semi-infinite object, it's a parabolic equation. The temperature decay exponentially. But the exponential decay means at t equals 0, you give the temperature on the surface a disturbance. Infinite away, there's a fin in there. Infinite small, but it's not 0. Right? So that means the heat is propagating faster than the speed of light. So that's a dilemma in the Fourier heat conduction equation. Right? And one of those approximation, the reason to one of the equation to answer this is modify this heat conduction equation as Q equals minus K dt dx. This is called the Cantonian equation. Okay. But I say, so there are hundreds of papers written on this because you have a new equation. There are always people are good at the math solving there. Okay. But I say this most of the time is not correct because say if you go to look at the Boltzmann equation here, right? You go to here. In fact, let's say you find that you can transform. You put a tau onto the other side. Oh my, here it should be a tau. Okay, otherwise the unit is not right, right? So you put a tau on this side. You integrate times the velocity times the h omega times density of state. So you integrate both sides, right? You will actually get this term. You get this term, That's this term here. And it's this term, you approximate it still with the Fourier law. Okay? So I say this is most of the time is academic exercise because when you have a very fast temperature process, your gradient, the gradient term, the spatial gradient that typically exists, and because of spatial gradient, you cannot approximate this term by the Fourier law. That's because we're doing df, we're replacing that gradient f by f0. Okay? So this is what I say. There are many PhD theses written on this. And I say that's a waste of time, unfortunately, and you have to really understand what you're doing when you deal with those. Okay, so comment. That's one comment. The next comment I want to make, I'm not going to go into the detail. It's all in the book. If you're interested, you can read. So what we have derived is a constitutive relation, right? The relation between temperature gradient, the heat flux, velocity gradient, shear stress, right? Electrochemical potential gradient, current. That's constitutive relation. And you can actually start with the Boltzmann equation, derive conservation equations. And if you recall, when you derive the Navier-Stokes equation for fluid flow, what you used before, or you derive heat conduction equation, you use the constitutive relation together with the energy and momentum balance conservation equations. That's how you derive those equations, right? And you can start from the Boltzmann equation, and you take the moment. Okay, F is the distribution function in phase space, right? So if you multiply by the mass per particle on both sides, and you integrate, you have to do a summation of over all the states on both sides, you will get mass conservation equation. Okay? And if you do, so this is the per particle, because when we do all the Navier-Stokes equation or heat conduction equation, we do not have any variable in the momentum space. It's a real space variable, right? So when we sum up all the momentum variable, you're taking the average on both sides of the mass, total mass, say any location there. And if you do your momentum, you put in the momentum per particle into the Boltzmann equation. And again, you average both sides. You will get at the left-hand side, you will have the convection term in the Navier-Stokes equation. On the right-hand side, you'll get the right-hand side of Navier-Stokes, say pressure and the Newton shear stress, the shear stress term, viscous term, right? But there you still have to put in the constitutive relation, right? So to get the Newton shear stress. So you see here, you still are using the approximation. Navier-Stokes equation is approximation because you approximate the Newton shear stress term there. And same you can do energy. So on this side, the fluids has more higher order. You can do higher order moments and their modification to Navier-Stokes equations. But what's interesting is you go to look at the history of electrical engineering, right? And in the 1980s, electrical engineers start doing the same thing, and they derive the electrohydrodynamic equation for electron transport. So you go to check the derivation. I think in my book there are reference to this. You check the derivation, and so in 1980 and the literature 1980, a lot of paper trying to solve electrohydrodynamic equation. And the reason for that is even at the time, the gate length is becoming smaller and people aware the size effects, so they went to electrohydrodynamic equation. And of course, if you look back, if I say that seems to be really not the right approach, because we know the Lewis-Stokes equation is not valid when the mean free path is, longer than the characteristic transport dimension, right? So when you do hydrodynamic, you're not solving that problem. You're still doing the local equilibrium, and of course, the high field there is a convection, so that those things may, so how the electron effect may be captured. So, and I do not think there are really many people nowadays solving electrohydrodynamic equation. But even you go to check, there's electron shear stress, electron temperature, very fuzzy. The discussion there were very fuzzy in the literature. And then you go to phonon, right? There are also phonon hydrodynamic equation. These were in Russian literature. And nobody has solved it. I haven't solved any solution. So you see there, the point is all related, right? And different fields has probably some field developed tools, and other people learn and apply to different problems. But you got to understand what are the bases when you apply it. So that's all on this chapter 6, which is really starting from the particle transport, and when we learned or the diffusion theory. And what we're moving on is looking into classical size effect. That's chapter 7. Okay, so now we want to look at the regime when those approximations are not valid, right? And we can start with a problem where I'm looking at the heat conduction. I do heat transfer now. Heat conduction along a thin film, freestanding thin film. Okay, and let's say the mean free path. We know the mean free path of photons. And then the mean free path is longer than the film thickness, d. Okay. Now even though let me first consider the transport along x direction. So my Q is flowing along the film, right? And even though the Q is flowing along the film, we know the photons go all directions, right? So photons, the momentum space, if it goes this direction, and the mean free path, if it's longer than the distance I draw here, you will collide with the boundary. And of course, once collide with the boundary, they will be scattered, reflected, right? And that depends on the boundary condition. Roughness, for example, at the boundary. We know when light hits the surface like your table here, it's a diffuse scatter. If you put a mirror there, it's a specular reflected. Reality may be somewhere in between. And this is, in fact, still nobody really knows what's happening at the boundary. Right? So the assumption we'll be doing first is a diffuse. So is isotropically scattered into all directions. And in this case, conceptually, you'll have worse heat conduction than when you don't have the boundary, because otherwise the heat will go from here. If say this is mean free path in bulk material, heat will go from here to here. That means at least the distance-wise in x direction is this distance. But now, because of diffuse scattering hit the boundary, half of them were going back much earlier, right? So those kind of size effect typically will impede your transport. And let's go to see what the equation tells us. I'm going to solve this equation, the Fourier law, and I have an x direction, and let's say the x direction is very long, it's not finite, but say y direction is finite, right? So we have, in this case, I have Vx dx plus, let's say here is y direction, Vy df dy. And z direction, I don't have a gradient, so I can drop that z. I'm only considering the x direction flow. So I have mass f0 steady state over tau. This is this is the equation I want to solve. And I'm going to again look at the at least say I have two directions, df dx in the x direction, right? So if I do g equals f minus f0, small say not lesser small deviation, but this is my difference there. And I substitute this into the equation here. What I get is Vx df0 dx, okay, and then dg dx. But the x direction, my variation is relatively small, right? I said the x direction I have very long. So that deviation dg dx can be dropped out. So what I have is Vx df0 dx and y direction. So df0 dx, f0 then is a function of x. I have 1D transport. So df0 dy also drops out. So what I have is a Vy dg dy and equals minus g over tau. Okay? So this is what I really am looking at is the variation because of the boundary. In the y direction, I have variation size dependence on the distribution. So different point, I have different f in the y direction. And so what I'm going to look at when I rewrite this equation, Vy dg dy plus g over tau, and that equals negative Vx df0 dt dx. So you can say if I do not keep the first term, that's essentially what I had before. I'm only keeping an extra term due to the constraint in the y direction. Okay? Now, you can solve this first order differential equation for g. And if it's a first order differential equation, how many boundary conditions you need? Yeah, somebody can speak out. You know it's only one, right? You need only one boundary condition. You need one boundary condition for any pair of Vx, Vy. Because Vx, Vy are random phase space variable. Right? So basically what it's saying is, you see here, any direction look at, this is the direction that they're propagating. And you need a boundary condition in this direction. And at any point, if it's an internal point, I have direction propagating 360 degree all space. And this one coming from here. So I need a boundary condition either on this surface or on this surface And if you can specify one surface for 360 degrees, let's say 4 pi solid angle, you're fine. Only start with one surface. But most of the time, because I have two constraints, and it's better to do for the one that traveling this from leaving this surface, I have boundary condition here, and for this half bottom. So that together gives me 4 pi solid space, real space. Okay, so now let's solve this, and Vy, and so this is at any point, right? This is a y direction and x direction. Any point, let's say this is a Vy, Vx, that's determine the propagation direction. And it's, again, your choice whether you use a Cartesian coordinate or use a spherical coordinate. Okay? And whether you put if you use a spherical coordinate, which direction you'd say this is your polar angle, which are the azimuthal angle. It's all your freedom. And for this problem, I'm going to do this one as my theta. Okay? And then say xz plane is as my azimuthal plane. So with that, I have, if again, so in this case, I assume V is isotropic. Okay, and real crystal, they are not isotropic. So I assume V is isotropic, so I have V cosine theta, that's Vy, and dg dy plus g equals, the right-hand side is a term that depends only on x, right? Vx is, say, Vx I have to be careful, it depends on theta phi, but doesn't depend on y. Okay? So I solve this equation, and the way I solve it, in fact, because this is a function of x, so you will say g mass S0x equals, it's a homogeneous equation. You do a new variable, g mass S0, and then it's a V cosine theta. So I have say exponential minus y V cosine theta. Right? That's my solution. And you plug in this back into here. You don't believe it, you can check. That should be 0. Okay? So this is my solution, and I said that we need a boundary condition, right? At y equals 0. At y equals 0, the boundary, if the boundary is diffuse, so it goes out isotropically, that corresponding to F0. This F going out is equal to F0. So G equals 0 at y equals 0, because F equals F0. So G equals 0, y equals 0. So I have C equals to S0. So what I have is G equals for theta at y equals 0. And this means theta is larger than, say, 0, less than 90 degrees. I have G equals S0 and exponential minus y V cosine theta minus 1. And cosine theta is also called directional cosine. Mu equals directional cosine theta. So that's just a symbol. So I can write in terms of mu rather than take the whole cosine theta. Okay, so this is for y equals 0. And similarly, you look at the upper plane, you will say G equals, again, S0 and exponential. If I look at this, will be D minus Y gamma. Oh, do I miss a tau? I should have a tau somewhere. I have tau. I should, let me do this. I put a tau on both sides. So I write the extra equation, tau y, tau dg, dy plus g equals minus tau vx df0 dt, dt dx. Okay, extra, so I put a g, so this is a tau. I have tau, so that should be tau. Tau times v is mean free path. Okay, so tau times v is mean free path, and divide that by mu and minus 1. And this is for theta is less than 180 degree, larger than 90 degree. And this is the flowing from leaving the first surface, the upper surface, into the medium. So what I have here, you can say this is the exponential decay because the cosine mu in 90 to 180 is negative. So this is always say it's from surface it decays, surface it decays. That's how I decide my sign. Physical, you can think about it in physical term. Okay, so I have the solution for G. That means I know my F, because F is F0 plus G. So once I know F, I can go to find out what's the heat transfer, right? So I can find out what's the heat transfer. My heat transfer through any plane of x is, I have to say this gives me any point along the y direction, right? So I sum up the flux integrate over y direction and integrate over y. So it's 0 to y, 0 to d over dy. And then my every flux, I still have what I have, Vx times h bar omega and times f. That's my, say, kx, ky, kz. This is where I started when I write the flux for all the transport. Now, because this quantity is a function of y, I integrate the y to get total, right? And now, you should be comfortable converting the summation into integration. And so what I have, 0 to d and dy. And the summation into integration, what I have is I'm using spherical coordinate theta, phi, and v. V is a constant, is my frequency. Say I'm eventually going to the frequency domain. So I have 0 to omega max d omega, and 0 to pi d phi, and 0 to pi d theta. And I have the rest is a Vx h bar omega f. Right? This f now is say f0 plus g, right? So g for different direction, I have different solution there. I have to split this 0 to pi integration into two terms, 0 to 90 degree, so I can use this g. 90 to 180 degree, I use the bottom g, right? Okay. And Vx, what's my Vx? My Vx, so now you see, because I took the easy x, y direction, theta and y direction, so I have to project that V into x direction. And that V, if I project it, remember it's a spherical coordinate, right? Vx is V times sine theta, that goes to azimuthal plane, xz direction. And the phi, the azimuthal angle, if I align to the x direction, that well, I have a cosine phi. So this one is v sine theta cosine phi. So this is Vx. And now when I do solid angle, is theta d theta d phi sine theta d theta d phi, right? When I do from Cartesian to spherical coordinate, I have sine theta d theta d phi, and then I have density of states divided by 4 pi, because that density of states was for the integrated whole solid angle, right? So this is the conversion I have to do, and at the end you see I have to do all those integrations. And this integration you cannot do if everything depends on frequency, relaxation time, because here S0 I have tau, I have another Vx. Okay, so actually I will get a Vx squared, right? So here I will have V squared sine theta squared cosine phi squared. Okay, otherwise you get 0. 0, if just cosine theta 0 to 2 pi, you get 0. But I have a square. Okay, and if you do your integration, I will skip the detail. What you have is here is I want you to really sit down and make up the missing derivations. But say I'm going to give you the result. You will see. And if say the tau and the v are constant, or you can say the tau times v equals mean free paths are constant. Okay, so here my condition is the mean free path is a constant. You go to fluids problem, right? When people do rarefied gas dynamics, they typically take constant tau. You do heat transfer, people typically do constant mean free path. I don't see a very good justification for those choices, but because of those different choices, the final result looks slightly different. Okay, and so if I do this, and of course eventually you can write this as your minus k, but because you integrate, so it's d dt dx, and this is effective thermal conductivity. And the end result of all the integration is k effective divided by k, which is the bulk, because in the solution we have the here df0 dt. This essentially also gives you the bulk thermal conductivity. So at the end, when I normalize it, I have k effective, k bulk equals 1 A3 Cos 1 minus E3 Cos minus E5 Cos. And this Cos is the long dimensional thickness divided by mean free path. And E is an exponential function equals defined as 0 to 1 mu n minus 2 exponential minus cos over mu d mu. So this is a function that in the past that people actually turbulate. It's an integral function of order n. So this is where I say if you take a constant relaxation time, you'll not get this En, you actually get a different exponential. That's where the difference are. Okay, so if you plot this effective thermal conductivity of materials, this is your Ksay, which is d over mean free path, right? And this is normalized effective over K bulk, let's say bulk. And it goes, so this happens when this transition goes to, this is of the order 1. You approach the bulk thermal conductivity when the material is very thick compared to mean free path. But this is small, you have the deviation from this mean free path. So these are the, in order for nanostructure, you will say those property eventually should go back to bulk when you make it thick enough. And then if you have a theory, you sanity check, right? When you go back to the bulk, say thickness, do you get the bulk properties? And so this solution is also called the fuchs-sondheimer solution. Sondheim or Sondheimer. Okay, now I'm putting a solution. And it was developed for electrical transport. So the original study was not on thermal conductivity, it was measuring the electric conductivity of films. That turns out to be smaller, and the solution is identical for electrical and thermal transport. So you can also say this could be the electric conductivity divided by the bulk electric conductivity, and the thickness divided by bulk electron mean free path. You all have the same behavior there. And this is because the surface scattering. But, okay, here we're assuming, just a comment, we're assuming that the film deposit is the same as material, bulk material. And very often this is actually not the case, because when you deposit a film, for example, you put a silver on silicon, what happens is it's not a single crystal, it's grains. So in fact, say the nucleation, when you deposit the material on top of the substrate, first you have a nucleation. So the atoms nucleate, they're small dots. And then, so there are a lot of small crystals. And when you further deposit it, some of the smaller crystals disappear. The larger crystal win. So your crystal grow larger and larger. So the grains actually, grain size is not constant. And in this case, what you measure is not just the surface effects, but the interface also, because the grain interface are scattering centers. So you just can't always say it's this effects that happens at the surface, the interface also. Okay? And the other comment is if you have a specular surface, you can again solve the equation, but the boundary condition change the boundary condition. And in this case, what you'll say is that the specular surface do not degrade your transport. You get a 1. The ratio approach 1. And the reason is, if you think about it, specular, even though there's a direction change, but there's still the same amount of, so this is the original go here, but here. So in terms of transport in the x direction, the same. There's no effect in scatter, the scatter. So it's sort of like a waveguide. You bounce your light in an optical fiber, as long as your fiber surface is specular for light, they go forward. Right? And there are also solutions for partially specular, partially diffuse. So all those are existing solutions. Okay, so in fact, the original observation, those are the classical size effects. And the first experiment was done by Casimir first theory was done by Casimir. So Casimir turns out to be, there are many Casimir effects. And one of those is on heat conduction, where he explained this Casimir effect based on, because there are some experiments on diamond, right? I showed before, I commented before, thermal conductivity of bulk material is always looking like this, right? At a very low temperature, it's proportional to specific heat. And that's because there's no internal scattering. The mean free path is limited by the boundaries. So those early experiments, the size effect was in 1920s. And Casimir had a theory, I think it was in 1920s. And actually, I forgot, it's 1920 or 1910, 1900, near that range. But say he was explaining those effects using the boundary scattering. So it's also Casimir's effect. One further comment, in fact, those are the things we're writing a paper on coherence, and I was thinking this weekend, where is this decoherence coming from, right? So if I have a film, we're looking at the in-plane direction, but the next one I'll talk about this direction, right? So if there's no scattering inside, the photon will propagate as a wave packet, right? But they don't get if there's no scattering, that wave packet will propagate as a wave. So the phase is actually maintained, right? So it's a coherent transport until it hits the surface. When it hits the surface, the Casimir treatment here is it completely diffuses out, right? So there your phase is randomized. And when you're randomized, when you come back, again, any of those photons that launched from any direction, that part is still coherent, but it's not interfering with this one that going out that direction because the phase are randomized. So these are the classical regime, classical size effect regime. Doesn't mean there's no phase coherence at all. So I think what I'll do next, you have heard a lot now, and really it's time to let's take a look at the recent literature. Now you look at it. Oh no, not this one. I would say that you probably, if you look carefully on those papers, you should be able to at least catch something that we talked in this class in many, many journals. I think it's good to look at let's take a look at the nano letters again. Oops. Okay, so I dare to say that now you should say look at over 50%. Some of those journals you should hear something, and you should not be afraid of looking at it. Graphene, okay. So maybe you have quantum transport, you have ballistic transport, and solar cell, okay, we are going to talk about the solar cell soon. But I mentioned, say, like some of those protein. Let's skip that. What do you think about this one? Huh? Single molecule directivity enhance the Raman scattering using nano antenna. So I would think that say Raman is probably related, might be related to surface plasma, where you got those nano antenna. There you have high energy density, localized density of states is high. So you will not be surprised if you read the density of states or those terminology when you look at the paper. And when you have a high local density of state for electromagnetic wave, you can have a higher Raman effects, right? And look more. My comment may not be right. You can open the paper and see what it's talking about. And that's when I do. I say, OK, anything interesting. Maybe that's not, I say enough of a lot of this stuff. So band-like transport in strongly coupled and doped quantum dot. What does it mean? So quantum dot has discrete energy levels. When you put them together, and the energy levels start to overlap and form new bands. That's my interpretation this paper is going to be talking about. Right? I didn't look at my guess. You should go back to check and see how correct, whether I said is correct or not. Selective gas sensing with single pristine graphene transistor. What's this about? Anybody can guess? So what happens is that when gas attached to the surface, you will change the charge inside. And you measure electric conductivity should change. And then when I look at title, okay, the question is whether you can tell which gas you're measuring. Right? You put any dirt on top, the conductivity will change. So the question is, can you tell which dirt it is? Right? When people do sensors, you have to be specific. I don't know what this one is doing, but I would assume it must be doing some tunneling or related. Direct image on single gold atom with nanowire. Maybe nanowire is a probe of the tunneling here. Again, I'm just guessing, okay? I want to challenge you to go back and to develop the habit and see whether there are things that you should be paying more attention to. This one they sent me. This is a work that Arun Majumdar and Pei Yang together, they've been working on this many years. And what they observe is that the thermal conductivity, some roughened wires, has a low thermal conductivity that cannot be explained by fuchs-sondheimer theory. There are many papers written on this. And some people say because they use this, they claim they have high ZT, silicon nanowires. And many people say that's not probably correct. So they spend a lot of time and recently found that the thermal conductivity actually correlates with the purity, the roughness, different purities. Here is the sort of, I forgot what is this, but they did the frequency analysis, like a fractal dimension, whether that's correct, whether that's a wave effect. So people are still, these are very positive. This is a positive result. You can say, so that's directly related to the failure of this one, what I just said. Okay, surface plasma. Modification of spontaneous emission, right? Surface plasma, again, you heard it. pulsar effect, pulsar factor is related to cavity, say, dynamics. Phononic band, right? Almost every paper you can make some comments now. That's my point, okay? We're chapter 7, we have 3 more chapters to go. And after that, they should be able to comment on 95% of the paper. Okay, go back, spend some time on it, and see what my guess, okay, is correct, and then you can make your own guess.